Welcome to this presentation. Unfortunately, my co-presenter is on his way. His flights, 2 different flights, have been delayed individually, so he'll be here just in time for the applause. I'm kidding. He's a great guy, and he'll be here presently. So we're a startup in Palo Alto. We are spun out of Stanford Research. I'm a professor in computer science, electrical engineering there. And what you'll hear about is how our technology can make LLM networks much more reliable and also much faster. Okay? So the most important thing to say about what we are offering is this piece of software that doesn't require any hardware support. It doesn't require any support from the network interface card, NIC, or the switches. And it works just off the shelf, and it's highly scalable. Okay? And what it enables at the first go is monitoring. Well, what we have works also for TCP plus Ethernet technology. We now, in the context of LLM networks and large-scale training clusters, it works for RoCE or RDMA over converged Ethernet and InfiniBand. And here we can measure the NIC to NIC, or the network one-way delay, very precisely, down to a sub-microsecond accuracy, and also monitor the health status of all the links. Are they live? Is a link dead? And because it turns out in these very high speed, high bandwidth, constantly running, like weeks, months on end type networks, the links can get hot because the optical transceivers, on either side of the link is for data communication can get hot. It's a laser in it, and that can make the 2 sides lose bit boundaries, and links can flap. That can happen at the edge of the network as well, and that's much worse. Okay, but we can monitor the status of this system continuously. And secondly, for the case where the network is not healthy, that is, a link is broken, we can route around it. We can find alternate paths and keep the job executing despite the failures. And this is very important, because if the link at the edge, that is the network interface card to the first top of the rack switch, fails, then without any remedy, the job will crash, the entire job. And if that happens, you not only incur the delay of waiting for the link to come back, but worse yet, you'll have to, even if you hot plug another machine, you'd have to roll back to a previous checkpoint, which could be as late as whatever your frequency of checkpoint is, okay? Or your period of checkpointing is 30 minutes, maybe, right? So the other thing we can do is fast job execution. So now that the network is running reliably, can we actually grab all the bandwidth that there's going? And the talk will present these, the system, and how it addresses these challenges. Okay? So here we go. And the impact of all of this is you really are looking at the model flop utilization, which is the number that matters for how well your cluster is doing its job. And the higher it is, the better it is. And this will lead directly to the completion time of your jobs. So how does LLM training work? Very brief recap. There's a cluster of servers carrying GPUs. And for example, one of the servers blown up will look like this. It has a CPU, typically 8 GPUs, and typically GPUs connected to 2 NICs. And there's also an Ethernet NIC for the CPU, what's called the front-end network. And the NICs are facing the RoCE or InfiniBand network, right? And this is true at all the servers, and then there's an interconnect fabric. And so initially, you will load up the data, training data from storage servers, and then processing will begin. And what that does, processing is lots of compute taking place with GPUs, and as the LLM is being trained and the weights are being calculated, that information is passed around from node to node on a ring typically, or it could also be a tree, binary tree typically, where the different components of the data that each GPU is working on is now being swapped through this ring, and you end up getting the communication part of this execution done, right? Now, underneath the hood, what's happening is, how does this data get exchanged? A GPU will emit a message. There's Jug. Hello. Please. So what happens underneath the hood is there's a message. The GPU emits a message, and this message is broken into chunks. Chunks are assigned to queue pairs or sockets in the case of TCP, but in the case of Rocky and InfiniBand, queue pairs. A queue pair is an association between two queues, and the queues are in the memory of either the GPU, in the case of GPU Direct, or in the CPU, and where the data will move directly bypassing the kernel. So the NIC will yank this data out of the sender and put it across the network into the receiver, and that's what's DMA, direct memory access, and remote DMA is, right? And so when we do this, the sending NIC is sending this, packetizes these chunks and then sends them over as Ethernet frames typically, and then and now the queue pairs play a second role. They're also, they have packet addresses that go with the queue pair ID, and that puts a queue pair onto a path in the network through the way network forwarding works. And there are several ways of doing it, and it'll get hashed onto one or more of the available paths, and that will then arrive at the receiver, and all the chunks of all the queue pairs are reassembled and then pushed into the message is reconstituted, and then that's directly placed into memory. Okay, so that's where we come in, right? So if you look at these arrows that I've shown that just say this is the network, what does it look like? It really is that entire interconnect is what's called a fat tree, and it's a layer of servers connected through to the top of the racks, and subsequently to spine switches to each other, and the queue pairs. What's going on is, think of the green queue pairs and the orange queue pairs. Queue pairs are colored because of their flow labels are different, so they'll follow different paths. That's what you should see. And so this server is talking to its neighbor on the ring, who then talks to his or her neighbor on the ring, its neighbor on the ring, and it keeps going around. And the servers are all talking, and they're all using different paths, different queue pairs, until the ring is closed. Okay, this could also be a binary tree, same story. But any edge in the network is decided by a queue pair label. Okay, and challenges with these sort of systems increase with scale. Okay, scale is sort of always difficult, always the enemy of simplicity. You have to start getting very complex. But here something particularly is the case. So think of it now not just one row of servers, but racks and racks and aisles of servers. So it gets difficult to get very precise network delays for 10K plus GPU clusters, right? So it's not really that easy. And if you want to keep the system working reliably, there are now many more components that can fail. And typically large clusters are running very large jobs and for very long times, and they generate lots of heat, and this is another thing that scale poses as a challenge. And contention of when these queue pairs meet each other on network paths and they'll contend for bandwidth, that also increases because there's just many more queue pairs and there are many more GPUs at NICs, right? So everything just gets exacerbated. So it's very easy to run 4, 8, 64 node type things, but start thinking of thousands of nodes, everything just gets complicated. My co-presenter, Jug, is one of the key people at OCI ensuring that all keeps running smoothly, right? Because it's non-trivial to design this stuff. So that's the challenge. The challenge is to keep everything working reliably while getting very good performance. Okay, that's really what the jobs want. Okay, so everything gets done sooner, and you can you can finish your job sooner while everything continues to be reliable and highly performant. So let's look at each of these things. First is monitoring. The goals for monitoring are the network links and paths healthy and operational? It really is this liveness check. And so detect broken paths at the queue pair level. Is a path live, or is a link on the path on the blink? And secondly, accurately measure delays. And as I said, we want to measure the network delay. So this is the NIC to NIC delays. Can we measure them? And then this is to answer questions like, is the path congested? A packet is getting delayed in buffers, okay? Or is the path, is there contention on the path? Are there, 2 or more queue pairs oversubscribing a path's bandwidth, okay? And so our solution to this problem is, first of all, we create this object called a probe mesh. A probe mesh is small probe packets traverse this. So a probe mesh is a set of edges that are starting from one NIC to its counterpart NICs at other servers, and that connects. This is just showing what the outbound edges look like from, let's say, one NIC at one server. So every NIC at every server is doing this, okay? And so this probe mesh is sort of, think of this as like a thing that's traversing all the network paths, and therefore the edges are shown here as going this way, but from the previous thing you should imagine them going through the network, right? And first thing you can do is monitor network's health with this probe mesh. Basically, the probes keep checking for the liveness of paths, whether on a particular path at a particular time there is data flowing on it or not. Okay, so this is just keep looking at all the paths, okay, and raise a flag or raise an alert if something is broken. And then the NIC to NIC delay measurement is synchronize the clocks first of all at all the NICs with a common reference, okay, and then a probe will go down this path. You take a timestamp at the transmitting NIC, and an ECN mark, perhaps, at the switch. ECN is explicit congestion notification. These are marks placed by switches whose buffers are getting slightly overoccupied. You can pick that congestion signal as well. And then pick the receive timestamp. Now, having both the transmit and receive timestamps and the clocks being highly synced, you end up having your one-way delay measurement, right? And that's really what you'll see being demonstrated to you shortly. Okay, and this is being done for every queue pair of interest. Can be done for any queue pair of interest. Okay, so and continuously. Okay, so the next thing I'll talk about before our first demo is, can we reliably operate the network despite link and NIC failures? And this is the demo. You'll see it as an OCI cluster. So where we can only fail the link attached to the edge because it's a sort of just failing the NIC. We can't touch the switches and the internal link, so we'll fail the edge link, which is actually the more severe case. So the problems are, there's a path like this, it's a queue pair, and it's possible that an internal link fails, or it's possible the edge link fails. And in both cases, what we'll do is find an alternate path to route the traffic around the broken path, okay? And what do the results look like? Again, this is on OCI. And so we have a 4-server cluster, 2 servers per rack, 2 racks. And what you'll see is a job that runs on these nodes, and it's going from one node to another node across the rack, so it's touching the spine layer. And the 3 cases are basically where there's no failure. This is status quo, right, on the left. And second one is where we don't have our solution, but the NIC fails. So at the point where the NIC fails is indicated on the graph, the job also dies. And when the NIC is revived, the job doesn't, the job stays dead, the job isn't reviving, okay? So this is pretty canonical. This happens, in the course of operation of these networks where the edge link fails. On the other hand, when you have our solution on, this is again this piece of software, if the edge link fails as shown the same place, the job continues to work at pretty much close to the previous high throughput, okay? Because we found some good alternate paths, and these are supporting the traffic of the failed NIC. And then when the original NIC revives, and this happens because, again, these links go on the blink. They're not like gone forever. So that when this hot lasers on either side and the temperatures, the bit boundaries are lost, they're reestablished. And when the reestablishing happens, the NIC comes back. The link comes back. And so you can revive the job. So this is a demo you'll see from my colleague, Vinay, shortly, right? So after that demo, where he'll show you both the probe mesh as well as the NIC failure case, he can, I'll come back and tell you more about this part. Okay, over to you, Vinay.
All right, so what we've got here is a live cluster that's actually running on OCI. And so as you can see, there are 4 nodes, Oracle 0, 1, 4, and 8. And each of these 4 nodes has 16 NICs inside. Those are the smaller boxes. So the first thing I'm going to talk about is the always-on probe mesh. This is a probe mesh that's set up between pairs of NICs that is continuously monitoring both the health of the network. This is an indication of the connectivity between the NICs, and also the quality of the paths, how much congestion is on them, what do the one-way delays look like. So if I click a NIC, I can see who all this NIC is talking to. In this case, its counterpart on all of the other nodes. Clicking an edge provides me with measurements of the one-way delays on the edge. So here we see the outbound and inbound one-way delays for this edge. An important thing to note here is that we're actually probing multiple different paths on this edge. So when data is sent between these 2 NICs, it could go any number of ways in the fat tree that Balaji was describing earlier. And we actually sampled those paths and have information about each and every one of them through this probe mesh. We can see here that right now there's no traffic running, so the delays are basically just the propagation time. I'm seeing about 2 microseconds right now because the 2 nodes that I've chosen are on different racks. So that's what this dotted line is representing. Oracle 0 and 1 here are under one top of rack switch, and Oracle 4 and 8 are under the other top of rack switch. If I select an edge that's within a top of rack switch, we have much smaller propagation time. It's about half of what it was, about a microsecond in this case. So now let's take a look at what happens if I actually stress the system a little bit and apply some traffic. So I'm going to start to all reduced jobs. And this is a common collective used in a lot of LLM training. So when I start these jobs, we'll see first here that they'll be labeled on our user interface. And one of the jobs is going to run between Oracle 0 and 4 across the rack. The other job is going to run between Oracle 1 and 8, also across the racks. We'll see the throughput increases because now there's a high volume of data being sent. And examining the one-way delays indicates that there is congestion in the network now. These red edges represent paths or links where the delays are high. We can see here as an example that as soon as I started the traffic, the delays shot up from the propagation time of a couple microseconds to about 15 microseconds on one of the paths, which is one of the paths that the traffic is actually colliding with right? So I can sample around the network and show a couple more examples of this. This is another edge where multiple pads are actually colliding with the traffic. And so we see that the delays on those pads are higher than they would have been just in the case of the base propagation time. So that's kind of an overview of the probe mesh. What I'll do now is I'll stop these jobs and, sorry, yeah. Oh yeah, sure. So these edges, as a point of reference, sorry, give me a second, are cases where the delays are actually pretty low. They didn't go up that much, and this is because the traffic isn't actually conflicting on these pads. Cool. So what I'll do now is prepare the next demo, which is to show Clockwork's solution of recovery for link flaps. So what I'll do first is I'll start a job that doesn't have Clockwork solution, just to establish a baseline for what happens when we're not turned on. So at the very beginning, all of the NICs are up, all of the NICs are healthy. So the moment that I turn on this job, traffic will start again, and the job will run at some throughput. So once again, this is an example of a collective that's commonly used in LLM training, which is all reduce. This collective is running between Oracle 0 and 4, and as you can see here, throughput shoots up. So I'll let this run for a second or two, and then what I'll do is I'll actually simulate a link failure. So this is something that commonly happens when the NICs get hot and will cause the job to actually crash. So on this, for this job, I'm going to kill one of the NICs on Oracle 0 right now to simulate the link failure. So what happens here is that the throughput now goes to 0. The job has essentially died, as denoted by this dotted gray edge. And an important thing to note is even if the NIC comes back after a certain point, it's not as though this particular collective will resume normal operation. Typically what will happen in LLM training is that you'll have to go back to an earlier checkpoint. So if, let's say you're checkpointing every 30 minutes, then you've essentially lost up to 30 minutes of compute as a result of this one potentially short-lived NIC flap. So when I bring this NIC back, that's exactly what happens. Nothing will happen because the job is dead and our solution isn't turned on. So now let me reset again and run with Clockwork solution enabled. So once again, I'm starting the job now with Clockwork solution and all of the NICs healthy. And once again, we'll see the throughput shoot up when the job begins. So the beginning of this is just like it was before. I just started the job. And now with our solution enabled, I'm going to fail one of the NICs, once again simulating a link failure that might occur during the course of training. So now, instead of the job terminating, what happens is it keeps running. And this is indicated by this throughput graph here. Whereas previously this went to 0, we're still continuing at a very decent throughput. And the moment that I turn the NIC back on, we'll continue resuming exactly as if nothing happened. Sure. Oh yeah, this NIC here is the failed one that's no longer active. So the moment I turn this back on, we'll see that the recovery process returns us to our original throughput and the job keeps continuing. so that's indicated by this transition here back to the original throughput. So yeah, that's the link failure and recovery demonstration. I'll hand it back over to Balaji to continue the next part of the talk.
So let's talk about, so we've just seen how to monitor the health and the quality, meaning the one-way delay congestion of the network at a fairly detailed queue pair path level, right? Then also Vinay showed you how you can continue to work if one or more components fails. Of course, at a diminished capacity because you lost capacity, but not crash, right? And this portion is about how can throughput, be for whatever is the capacity. Let's imagine nothing's failed, everything's available. How can we get the best throughput from this system as a network? This is just a question we ask of any network, right? So in particular, these networks. And these networks have peculiar sort of problems because of the coordinated way in which these jobs run, right? So that causes, anytime, things are coordinated, congestion happens. The coordination is the enemy of congestion, right? But this is the nature of these jobs, okay? So it's particularly interesting if you're a congestion enthusiast, right, like myself. So let's look at this contention. What happens, right? So as I said before, there are two two pairs of nodes communicating, and the green and the brown or orange queue pairs end up meeting at a link in the network. As indicated, the flows are contending for the bandwidth on that downlink from spine to top of the rack, right? And this is happening all the time in these networks, right? And since this is part of how network design has taken place over the years, this sort of thing, people understand how to look at it. So but in particular, it's not only endemic to FAT3, this happens when multiple senders, when multiple paths between a sender and receiver, and the flows are hashed onto these paths to exploit all the available bandwidth. That's what you'd like to do with a FAT3. That's the benefit of a FAT3. But when different senders are doing this at the same time, unbeknownst to each other, well, then their flows will collide, okay? And it's particularly bad when you're doing the LLM training, like I said, because everything just runs in a coordinated fashion. And since, every networking expert knows this, namely that there are several ways of coping with path contention. And one of the common ways is called equal cost multipathing, or ECMP. And what it does is, because these packets are bearing flow labels, and so the green flows packets all have the same flow label. And that decides what path they're on. It decides who's sending it, who's receiving it, and other information, and that decides the path. That's what the hash functions are working on. And this equal cost multipathing says, well, I don't have to put, I'm sending a bunch of flows from this sender to that receiver on these different queue pairs. I'll try and spread them out. If I do that, then I'm going to get more bandwidth. Instead of sending everything on the same path and just not utilizing what's available, I'll send them spread out. That's really the main idea of equal cost multipathing. And contention between flows persists because, since the labels don't change, and once these, in the case of the figure I've shown you, the green and the orange flows collide, they'll keep on doing that, okay? And so there's nothing that alleviates it. But the positive is, because just based on flow labels, and basically the source and destination addresses on the flow labels, you can think of this as a source-based route choice, okay? Or source-dependent route choice. And recently, there's another idea called DLB, or dynamic load balancing, that has been used in these type of networks. And what switches do, this is more of a switch-centric approach, what switches do is dynamically load balance by rehashing the flows. So the top of the rack sort of hashes flows, and then the spine levels are doing the same thing. But they do it not, a flow doesn't continue to stay on the same path. So it's not sort of running into other flows and just getting stuck in these local minima indefinitely. By just shuffling, they're sort of making the green and the orange flows, break apart, right? This is really the key thing that the switches are doing. And so obviously it's superior to ECMP, because ECMP is just a static thing, and DLB can actually be thought of. It's also hash function based, so you can think of what is dynamic version of ECMP. Okay, but one thing about DLB is that it needs to propagate the link state. If in the world where links fail, the link state has to be, because that switch now has diminished capacity, that has to propagate. And there are ways of doing this, but as you can imagine with scale, this sort of thing gets tricky on its own. So what we do is really ECMP, but something has to be done. ECMP, we know it doesn't work. And so what we do is we don't change the paths like DLB. We just change the amount of flow in the paths. Okay? So you have to know that this path has got contention on it, and this path does not have contention on it. So I want to move some flow from this contending path to this non-contending path. So in figure, what that'll look like is going back to this green and orange guys, right? So we've identified the middle link between the spine and the top of the rack as where contention is happening. And so what we can say is, well, we can identify it because of the ability to measure it. And then we can say the other paths are not contending. So we can move the flow from the middle to the sides, right? So this is basically what we do. Okay, it's dynamically detecting contention and dynamically reallocating the load, right, on the available paths. So you sort of just, snaking through the whole fat tree by just, avoiding all the hotspots, right? Because we can visualize, or our solution can, the monitor can tell where the hotspots are and where they aren't. Okay, that's the key. So how does this work? Okay. So again, in the Oracle testbed, which Jug and his colleagues have kindly enabled ECMP for us, because the default thing would be dynamic load balancing. So we have one cluster of each kind. So in this cluster, what we have is 3 different scenarios. These are all nickel primitives or collective, where two all-reduce jobs going across the 2 racks are triggered simultaneously. That causes a lot of path contention, and standard ECMP won't do well, and we'll show how we can improve that. Okay, and each of these 3 cases, that's what you're going to see, and it's exactly the same setup as you saw before. Because now ECN thresholds exist and they will kick in. You can also see some numbers on what the thresholds look like. Okay, so the first of the 3, 2 all-reduced jobs. The first one starts, gets 91 gigabits per second. There could be a small amount of contention already with just one job, right? Because it's only half the bandwidth used, but then it's just ECMP. Could be unluckily getting some of these guys colliding. But let's go to the bottom. When only one job is on, you can see the one-way delays that we're able to measure are very small. There's not much contention going on. Okay? If anything, it'll be something so negligible that it's not even worth addressing. But as soon as the second one starts, not only is the bandwidth, it's bringing down the first because they're both contending now. This is like the green and the orange guys, they're hitting each other. You can see the delays have gone up, right, immediately. And these delays are, a few tens of microseconds. And because we detected that, and we turn on the control, very quickly you can bring up the bandwidth, and the one-way delays are brought down, right? So this is sort of the bottom part is how the measurement of or detection of congestion is being done, and the top is what the remedy looks like. Okay, so basically, with our solution, we can give about the same bandwidth as you will get as if in this particular example, there's twice the bandwidth that you need than the full bisection bandwidth. I'm just merely talking about the right-hand side part and the first one. Okay, just from a numerical value sense. Okay, second is one of the all-reduce jobs continues in this all-to-all job. The all-to-alls, for those of you who know this stuff, is sort of the big bugaboo of all the collectives in the collective library. okay? Because everybody's talking to everybody, and then obviously that's the recipe for contention, and everybody's doing it at the same time, okay? So it's not just everybody's talking to everybody, and they're all talking to each other at the same time, okay? This could be one of those movie scenes where everybody's talking to some noisy family at the same time, right? That's what all-to-all is like. All right, so what happens here is first job comes 91 gigabits per second, not much congestion, as seen at the bottom. Second job comes, so all reduce is running first, all-to-all comes. All-to-all, as you can see, is already doing poorly compared to all reduce. Delays have shot up, and now when we are turned on, everything goes back to being normal, delays are subdued. And the final one is what happens when you have two all-to-alls. In this case, the first all-to-all itself doesn't do as well, because as I said, it's an all-to-all, and even though there's only one of it. And you can see some delays on some paths is already elevated. Some queue pairs are hugging the x-axis, there is not much delay. Some are already experiencing elevated delays, right? The second one starts, everything is gone down, and then when we're back on, we can improve both of them, okay? And again, the delays have gone away. This is really the refrain here, right? So, because we have two clusters, it's worthwhile to just ask, how does this look? DLB does pretty well, is the short of it, in the sense, compared to traditional ECMP, right? This is DLB, because it's dynamically load balancing, so when there are two jobs, like this is, this bottom portion in the middle, when the second all reduce comes, that is traditional ECMP. Relative to this one, which is hovering around 45 gigabits per second, clearly DLB is twice as good, right? So it's a good algorithm in that sense. Of course, when you turn us on and we do the ECMP plus our thing, we improve over DLB, but in this case modestly. Nevertheless, we're not stuck in the ECMP local minima rut, okay? This one is the all-to-all. One of the flows is now an all-to-all. As before, traditional ECMP doesn't do well, but it's also DLB itself. All-to-all is just going to give everybody a hard time. In this case, DLB, okay? And however, with ECMP and our sort of flow balancing, dynamically detecting congestion and balancing, so as to account for them, we can do much better. And the last one is what happens when there are two all-to-alls. Again, in summary, standard ECMP doesn't do well. DLB is also hurt, but we can do better than even the original single job. So from this, you might even say we sort of have more than 2x the speed up, meaning one job running on the whole infrastructure is like 50% utilization roughly, right? And already that's at 84 gigabits per second or whatever that number is. We're already able to get 92 when both the jobs are running. So this is sort of what we've been working on. I'm really happy to share that with you. And in the last couple of minutes, because we're up on the hour, I'm actually going to invite Jug Brar from OCI to, we have demos and stuff, but in the interest of time, I want to invite Jug to join me here. And Jug, really, thanks a lot for giving us, yeah.
Cool, thank you, Balaji. So in closing, I'll just make a couple of comments and observations. Firstly, it's a good day when you have a problem and a startup comes along and promises to solve the problem. That's a lucky day. So I'm personally, at a personal engineer level, I'm really excited to be working or collaborating with Balaji and team. And I have high hopes for future. Because I'm a technology guy, and I like technology because I think it's a powerful weapon for solving problems. Weapon is the wrong word, tool for solving problems. And hopefully this is that. And I'll make a couple other observations. Balaji and Vinay made it sound like a really simple thing to solve. This is not a simple problem to solve. I'm sure everybody in the room can appreciate how hard these problems are. These are not at all easy problems. Anybody who understands networking realizes these are hard problems. All cloud providers, all infrastructure teams in the industry have these problems. Those that claim they don't are either guilty, these are my words, guilty of lying or not paying attention. Everyone have these problems. I have a talk later today at 2:45 with Pradeep Vincent, where we will describe some of these problems. So these are really interesting, important problems to solve. This is really good work. I think this is great stuff. And by the way, Balaji, his work lies at the bottom, at the very foundation of congestion control for Rocky in the form of QCN and DCQCN. So I'm glad he's come back to put the cherry on the top. But yeah, I think this is great work.
Well,
thank you. Yeah, thank you.
Doing all the work, in fact. Thanks a lot, John. I really appreciate all the help you've given us with understanding the space of problems and solving them. Thank you, everybody. Thanks for joining us today. There's a booth, and the demos of some of these things, including the UI and other things, you can take a look. Reach out to us if you have any further questions. Thank you.